Chapter 7 Radar Navigation. Radar principles in the hands of the skilled operator. Radar provides precise updates to dead reckoning, Doctor, for navigation. At cruising altitudes, it provides information on land and water characteristics, as well as hazardous weather conditions over hundreds of miles around the aircraft. At low level, it provides detailed terrain information used to navigate at high speed over changing courses. It is adapted to terrain avoidance and terrain following equipment. Radar is a source of track and drift angle (DA) information for wind computations. The basis of the system has been known theoretically since 1888, when Heinrich Hertz successfully demonstrated the transfer of electromagnetic energy in space and showed that such energy is capable of reflection. The transmission of electromagnetic energy between 2 points was developed as radio, but it was not until 1922 that practical use of the reflection properties of such energy was conceived. The idea of measuring the elapsed time between the transmission of a radio signal and receipt of its reflected echo from a surface originated nearly simultaneously in the United States and England. In the United States, two scientists working with air-to-ground signals noticed that ships moving in the nearby Potomac River distorted the pattern of these signals. In 1925, the same scientists were able to measure the time required for a short burst, or pulse, of radio energy to travel to the ionosphere and return. Following this success, it was realized the radar principle could be applied to the detection of other objects, including ships and aircraft. By the beginning of World War II, the Army and Navy had developed equipment appropriate to their respective fields. During and following the war, the rapid advance in theory and technological skill brought improvements and additional applications of the early equipment. It is now possible to measure accurately the distance and direction of a reflecting surface in space, whether it is an aircraft, ship, hurricane, or prominent feature of the terrain, even under conditions of darkness or restricted visibility. For these reasons, radar has become a valuable navigational tool. As noted previously, the fundamental principle of radar may be likened to that of relating sound to its echo. Thus, a ship sometimes determines its distance from a cliff at the water's edge by blowing its whistle and timing the interval until the echo is received. The same principle applies to radar, which uses the reflected echo of electromagnetic radiation traveling at the speed of light. This speed is approximately 162,000 nautical miles, nm, per second. It may also be expressed as 985 feet per microsecond. If the interval between the transmission of the signal and return of the echo is 200 microseconds, the distance to the target is 985 times 200 equals 98,500 feet equals 16.2 nautical miles. 2 Radar set components. The principle of radar is accomplished by developing a pulse of microwave energy that is transmitted from the aircraft and is reflected by objects in its path. The reflected pulse is amplified and converted by the receiver for display on the display. The timing unit, or synchronizer, synchronizes all the actions in the set. To this basic unit, improvements are added for special purposes, such as weather avoidance, filtering, and terrain following. Components: the receiver and transmitter are usually one unit, the RT, with separate functions that, for this description, are dealt with separately. Figure 7.1, Radar system components. The transmitter produces the radio frequency, RF, energy using magnetrons. A magnetron generates radar pulses by bunching electrons using alternately charged grids that the electrons travel past. The spurts of energy are of high power and short duration. The energy is released at intervals, the pulse recurrence rate determined by the selected operating range. The generated pulse travels through either coaxial cable or, more frequently, a hollow tube called the waveguide. The waveguide requires pressurization to ensure the maintenance of conditions for proper microwave conduction. The energy passes an electronic switching device that directs outgoing pulses to the antenna and incoming pulses from the antenna to the receiver. The antenna is a parabolic dish with a protruding waveguide. It is gimbal mounted to allow rotation of the dish and, in most cases, to allow stabilization of the dish relative to the Earth's surface when the aircraft turns. Rotation of the antenna could be through 360 degrees or in a sector, either variable or preset. The 360 degrees rotation, or scan, is usually for mapping, whereas a sector is used in aircraft with limited space for the antenna or where the intent is to concentrate energy in a small area. The antenna assembly is either permanently locked to the longitudinal axis of the aircraft, bore-sighted, or only so aligned when stabilization units are inactive. When not caged, the antenna stabilization is accomplished by using gyroservo mechanisms. A sensor system that provides information to a computer keeps the antenna radiation plane parallel to the Earth even when the aircraft is in a climb or a bank. There are 2 radiation patterns popular in airborne radar design: fan and pencil beams. The fan beam is a wide pattern that distributes the RF energy across the beam in proportion to the distance it must travel. Figure 7.2, the fan beam is best for general mapping. To concentrate the energy emitted, the pencil beam antenna is used. The pencil beam dish allows scanning for weather or aircraft while eliminating ground clutter. It can be used to put more energy on a section of ground to increase returns. The antenna can be manipulated to aim the emissions through a control that tilts the dish from the horizontal plane. At cruising altitudes, in the mapping mode, it is sufficient to slightly tilt the dish down, but tilt should be constantly adjusted for optimum returns. After transmission, the reflected energy is directed back to the waveguide where it travels past the switching device that directs the returns to the receiver. The receiver converts the microwave returns to electrical signals that are amplified and sent to a display called the Planned Position Indicator, PPI. The amplification of the returns is controllable through a gain circuit. Depending on the type of return desired on the display, the operator adjusts the receiver gain. Other booster circuits, such as sweep intensity or video gain, are available, but operation of the receiver is most important. If adequate receiver amplification of weak returns is not applied, no amount of later stage adjustments put the target on the scope. The display or scope offers both range and azimuth information about targets to the operator. This information is relative to the aircraft's position, which can be referenced at either the center of the scope or offset to the side of the screen. Figure 7.3, the controls manipulates the display so that returns can be presented on the scope in their correct position relative to the observer. Figure 7.4, applying a polarization to the signals going to a display produces the actual presentation of the return. The null return has a predominantly positive charge, therefore, the trace is suppressed. A polarization shift is produced in the current to produce a blooming of the trace corresponding to the strength and position of the received signal. Range is determined by the travel time of a pulse from and back to the RT unit. Knowing that RF energy travels at the constant speed of light, range determination is simple. The synchronizer coordinates its display on the display. At the same instant that the timer triggers the transmitter, it also sends a trigger signal to the indicator. Here, a circuit is actuated that causes the current in the deflection coils to rise. At a linear, uniform rate, the rising current, in turn, causes the spot to be deflected radially outward from the center of the scope. The spot traces a faint line on the scope. This line is called the sweep. If no echo is received, the intensity of the sweep remains uniform throughout its entire length. However, if an echo is returned, it is so applied to the display that it intensifies the spot and momentarily brightens a segment of the sweep relative to the size of the target. Since the sweep is linear and begins with the emission of the transmitted pulse, the point at which the echo brightens the sweep is an indication of the range to the object causing the echo. The progressive positions of the pulse in space also indicate the corresponding positions of the electron beam as it sweeps across the face of the display. If the radius of the scope represents 40 miles and then the return appears at 3/4 of the distance from the center of the scope to its periphery, the target is represented as being about 30 miles away. In the preceding example, the radar is set for a 40-mile range operation. The sweep circuits operates only for an equivalent time interval so that targets beyond 40 miles do not appear on the scope. The time equivalent to 40 miles of radar range is only 496 microseconds, 496 times 10 to 6 seconds. Thus, 496 microseconds after a pulse is transmitted, plus an additional period of perhaps 100 microseconds to allow the sweep circuits to recover, the radar is ready to transmit the next pulse. The actual pulse repetition rate in this example is about 800 pulses per second. The return, therefore, appears in virtually the same position along the sweep as each successive pulse is transmitted, even though the aircraft and the target are moving at appreciable speeds. At times, the display does not display targets across the entire range selected on the scope. In these cases, atmospheric refraction and the line of sight, LOS, characteristics of radar energy have affected the effective range of the set. The following formula can determine the radar's range in these situations where D is distance and H is the aircraft altitude. D equals 1.23 H. Azimuth measurement is achieved by synchronizing the deflection coil with the antenna. In the basic radar unit, when the antenna is pointed directly off the nose of the aircraft, the deflection coils are aligned to fire the trace at the 12 o'clock position on the scope. As the antenna rotates, the deflection coil moves at the same rate. Relative target presentations are displayed as the sweep rotation is combined with the range display. Scope interpretation: the display presents a map-like picture of the terrain below and around the aircraft. Just as map reading skill is largely dependent upon the ability to correlate what is seen on the ground with the symbols on the chart, so the art of scope presentation analysis is largely dependent upon the ability to correlate what is seen on the scope with the chart symbols. Application of the concept of radar reflection and an understanding of how received signals are displayed on the display are prerequisites to scope interpretation. Furthermore, knowledge of these factors applied in reverse enables the navigator to predict the probable radar scope appearance of any area. Factors affecting reflection. A target's ability to reflect energy is based on the target's composition, size, and the radar beam's angle of reflection. Figure 7.5, the range of the target from the aircraft is definitive in the quantity of returned energy. The range of a target produces an inverse effect on the target's radar cross-section, and there is some atmospheric attenuation of the pulse proportional to the distance that the energy must travel. Generally, all four factors contribute to the displayed return. A single factor can, in some cases, either prevent a target from reflecting sufficient energy for detection or cause a disproportionate excess of reflected energy to be received and displayed. The following are general rules of radar scope interpretation. 1. The greatest return potential exists when the radar beam forms a horizontal right angle with the frontal portion of the reflector. 2. Radar return potential is roughly proportional to the target size and the reflective properties, density, of the target. 3. Radar return potential is greatest within the zone of the greatest radiation pattern of the antenna. 4. Radar return potential decreases as altitude increases, because the vertical reflection angle becomes more and more removed from the optimum. There are many exceptions to this general rule since there are many structures that may present better reflection from roof surfaces than from frontal surfaces, or in the case of weather. 5. Radar return potential decreases as range increases because of the greater beam width at long ranges and because of atmospheric attenuation. Note, all of the factors affecting reflection must be considered to determine the radar return potential. Typical radar returns from land. All land surfaces present minute irregular parts of the total surface for a reflection of the radar beam, thus, there is usually a certain amount of radar return from all land areas. The amount of return varies considerably according to the nature of the land surface scanned. This variance is caused by the difference in reflecting materials of which the land area is composed and the texture of the land surface. These are the primary factors governing the total radar return from specific land areas. Flat land, a certain amount of any surface, however flat in the overall view, is irregular enough to reflect the radar beam. Surfaces that are apparently flat are actually textured and may cause returns on the scope. Ordinary soil absorbs some of the radar energy. The return that emanates from this type of surface is not strong. Irregularly textured land areas present more surface to the radar beam than flat land and cause more return. The returns from irregularly textured land areas are most intense when the radar beam scans the ridges or similar features at a right angle. This effect is particularly helpful in detecting riverbeds, gullies, or other sharp breaks in the surface height. At times, in desolate areas that are flat, these occasional surface changes are apparent where it would not have appeared in more irregular topography. Such returns provide recognizable targets in otherwise sparse circumstances. In other cases, especially at low level over broken terrain, this effect could complicate scope interpretation. Hills and mountains normally give more radar returns than flat land, because the radar beam is more nearly perpendicular to the sides of these features. The typical return is a bright return from the near side of the feature and an area of no return on the far side. The area of no return, called a mountain shadow, exists because the radar beam cannot penetrate the mountain and its lost transmission does not allow it to intercept targets behind the mountain. Figure 7.6, the shadow area varies in size, depending upon the height of the aircraft with respect to the mountain. As an aircraft approaches a mountain, the shadow area becomes smaller at higher altitudes. Furthermore, the shape of the shadow area and the brightness of the return from the peak varies as the aircraft's position changes. As the aircraft closes on the mountainous area, shadows may disappear completely as the beam covers the entire surface area. At this point, a great deal of energy is reflected back at the antenna and recognizable features in that area are rare. Recognition of mountain shadow is important because any target in the area behind the mountain cannot be seen on the scope. In areas with isolated high peaks or mountain ridges, contour navigation may be possible, because the returns from such features assume an almost three-dimensional appearance. This allows specific peaks to be identified. In more rugged mountainous areas, however, there may be so many mountains with resulting return and shadow areas that contour navigation is almost impossible. But these mountainous areas are composed of patches of mountains or hills, each having different relative sizes and shapes and relative positions from other patches. By observing these relationships on a chart, general aircraft positioning is feasible. Coastlines and riverbanks. The contrast between water and land is very sharp, so that the configuration of coasts and lakes are seen with map-like clarity in most cases. Figure 7.7, when the radar beam scans the banks of a river, lake, or larger body of water, there is little or no return from the water surface itself, but there is usually a return from the adjoining land. The more rugged the bank or coastline, the more returns are experienced. In cases where there are wide, smooth mud flats or sandy beaches, the exact definition of the coastline requires careful tuning. Since both mountains and lakes present a dark area on the scope, it is sometimes easy to mistake a mountain shadow for a lake. This is particularly true when navigating in mountainous areas that also contain lakes. One difference between returns from mountain areas and lakes is that returns from mountains are bright on the near side and dark on the far side, while returns from lakes are of more uniform brightness all around the edges. Another characteristic of mountain returns is that the no-show area changes its shape and position quite rapidly as the aircraft moves. Returns from lakes change inconsequentially. Cultural returns. The overall size and shape of the radar return from any given city can usually be determined with a fair degree of accuracy by referring to a current map of the area. Figure 7.7, however, the brightness of one cultural area as compared to another may vary greatly, and this variance can hardly be forecasted by reference to the navigation chart. In general, due to the collection of dense materials therein, urban and suburban areas generate strong returns, although the industrial and commercial centers of the cities produce a much greater brightness than the outlying residential areas. Many isolated or small groups of structures create radar returns. The size and brightness of the radar returns these features produce are dependent on their construction. If these structures are not plotted on the navigation charts, they are of no navigational value. However, some of them give very strong returns, such as large concrete dams and steel bridges. If any are plotted on the chart and can be properly identified, they can provide valuable navigational assistance. Weather returns. Cloud returns that appear on the scope are of interest for two reasons. First, since the brightness of a given cloud return is an indication of the intensity of the weather within the cloud, intense weather areas can be avoided by directing the pilot through the areas of least intensity or by circumnavigating the entire cloud return. Figure 7.8. Second, cloud returns obscure useful natural and cultural features on the ground. They may also be falsely identified as a ground feature that can lead to gross errors in radar fixing. Clouds must be reasonably large to create a return on the scope. However, size alone is not the sole determining factor. The one really important characteristic that causes clouds to create radar returns is the size of the water droplets forming them. Radar waves are reflected from large rain droplets and hail that fall through the atmosphere or are suspended in the clouds by strong vertical air currents. Thunderstorms are characterized by strong vertical air currents, therefore, they give very strong radar returns. Cloud returns may be identified as follows. Brightness varies considerably, but the average brightness is greater than a normal ground return. Returns generally present a hazy, fuzzy appearance around their edges. Returns often produce shadow areas similar to mountain shadows, because the radar beam does not penetrate clouds completely. Returns do not fade away as the antenna tilt is raised, but ground returns do tend to decrease in intensity with an increase in antenna tilt. Returns can appear in the altitude hole when altitude delay is not used and the distance to the cloud is less than the altitude. Effects of snow and ice. The effects of snow and ice are similar to the effect of water. If a land area is covered to any great depth with snow, 1. Some of the radar beam reflects from the snow, and 2. Some of the energy is absorbed by the snow. The overall effect is to reduce the return that would normally come from the snow blanketed area. Ice reacts in a slightly different manner, depending upon its roughness. If an ice coating on a body of water remains smooth, the return appears approximately the same as a water return. However, if the ice is formed in irregular patterns, the returns created are comparable to terrain features of commensurate size. For example, ice ridges or ice mountains would create returns comparable to ground embankments or mountains, respectively. Also, offshore ice flows tend to disguise the true shape of a coastline so that the coastline may appear vastly different in winter as compared to summer. This phenomenon is termed Arctic reversal, because the resultant display is often the opposite of the anticipated display. Inherent scope errors. Another factor that must be considered in radar scope interpretation is the inherent distortion of the radar display. This distortion is present to a greater or lesser degree in every radar set, depending upon its design. Inherent scope errors may be attributed to 3 causes: width of beam, the length, time duration of the transmitted pulse, and the diameter of the electron spot. Beam width error is not overly significant in radar navigation. Since the distortion is essentially symmetrical, it may be nullified by bisecting the return with the bearing cursor when a bearing is measured. Reducing the receiver gain control also lessens beam width distortion. Pulse length error. Pulse length error is caused by the fact that the radar transmission is not instantaneous but lasts for a brief period of time. There is a distortion in the range depiction on the far side of the reflector, and this pulse length error is equal to the range equivalent of 1/2 of the pulse time. Since pulse length error occurs on the far side of the return, it may be nullified by reading the range to, and plotting from, the near side of a reflecting target when taking radar ranges. Spot size error. Spot size error is caused by the fact that the electron beam that displays the returns on the scope has a definite physical diameter. No return that appears on the scope can be smaller than the diameter of the beam. Furthermore, a part of the glow produced when the electron beam strikes the phosphorescent coating of the display radiates laterally across the scope. As a result of these two factors, all returns displayed on the scope appear to be slightly larger in size than they actually are. Spot size distortion may be reduced by using the lowest practicable receiver gain, video gain, and bias settings, and by keeping the operating range at a minimum so that the area represented by each spot is kept at a minimum. Further, the operator should check the focus control for optimum setting. Total distortion. For navigational purposes, these errors are often negligible. However, the radar navigator should realize that they do exist and that optimum radar accuracy demands that they be taken into account. They are usually most significant when the target is a thin no-show river, when it is very reflective but small, or when it is in close proximity to another show target. Thin no-shows are erased except for their wider points. With tiny, but very reflective targets, the cross-section of the return would normally be negligible on the display. Their extremely strong reflectance, coupled with the inherent errors, causes them to appear larger and of seemingly more significance on the indicator. When show targets are close to each other, these errors cause them to blend together, diminishing the scope resolution. Generally, the combined effects of the inherent errors cause reflecting targets to appear larger and non-reflecting targets to dwindle. Figure 7.9, Radar Enhancements. Variable range marker and crosshairs. Most radar sets provide a range marker that may be moved within certain limits by the radar operator. This variable range marker permits more accurate measurement of range, because the marker can be positioned more accurately on the scope. Furthermore, visual interpolation of range is simplified when using the variable range marker. On many radar sets, an electronic azimuth marker has been added to the variable range marker to facilitate fixing. The intersection of the azimuth marker and the variable range marker is defined as radar crosshairs. Altitude delay. It is obvious that the ground directly beneath the aircraft is the closest reflecting object. Therefore, the first return that can appear on the scope is from this ground point. Since it takes some finite period of time for the radar pulses to travel to the ground and back, it follows that the sweep must travel some finite distance radially from the center of the scope before it displays the first return. Consequently, a hole appears in the center of the scope within which no ground returns can appear. Since the size of this hole is proportional to altitude, its radius can be used to estimate altitude. If the radius of the altitude hole is 12,000 feet, the absolute altitude of the aircraft is about 12,000 feet. Although the altitude hole may be used to estimate altitude, it occupies a large portion of the scope face, especially when the aircraft is flying at a high altitude and using a short range. Figure 7.10, in this particular case, the range selector switch is set for a 50/10 mile range presentation. Without altitude delay, the return shown on the inside part of the scope consists of the altitude hole, and the return shown on the remaining part is a badly distorted presentation of all of the terrain below the aircraft. Many radar sets incorporate an altitude delay circuit that permits the removal of the altitude hole. This is accomplished by delaying the start of the sweep until the radar pulse has had time to travel to the ground point directly below the aircraft and back. Hence, the name altitude delay circuit. The altitude delay circuit also minimizes distortion and makes it possible for the radar scope to present a ground picture that preserves the actual relationships between the various ground objects. Sweep delay is a feature that delays the start of the sweep until after the radar pulse has had time to travel some distance into space. In this respect, it is very similar to altitude delay. The use of sweep delay enables the radar operator to obtain an enlarged view of areas at extended ranges. For example, two targets that are 75 miles from the aircraft can only be displayed on the scope if a range scale greater than 75 miles is being used. On the 100-mile range scale, the two targets might appear very small and close together. By introducing 50 miles of sweep delay, the display of the two targets is enlarged. Figure 7.11, the more this range is reduced, the greater the enlarging effect. On some sets, the range displayed during sweep delay operation is fixed by the design of the set and cannot be adjusted by the operator. ISO-echo detecting hazardous weather is not difficult in the normal mapping mode with most radar units. The weather mode offers increased sensitivity to weather phenomenon. But to discriminate between areas of varying hazards presents a dilemma. Reflected energy from weather is dependent on the density of the rain and hail it contains. The limitations of display capabilities to display these dynamic characteristics make detection of the more intense areas difficult. Also, computer circuitry is more effective at judging slight variations in shading than the human eye. The ISO echo control compensates for this deficiency by presenting a void area on the display corresponding to a hazardous area in the weather environment. This void area, the black hole, is dependent on a control that the operator sets to define the intensity of the area that is to be avoided. For instance, say only the largest cells of weather are desired to be displayed. The operator would set the appropriate control and, on the display, the weather depiction would be present. The areas within the weather where the most hazardous cells were located would be no-show areas or black holes. The ISO echo circuits are capable of sensing the variation in the received signals and act like a radio squelch control to block presentation of selected intensities. Figure 7.12, a word of caution, the ISO echo is not selective in the targets it blocks. If ground returns are received by the radar and a portion of their intensity falls into the range selected to be blocked, they too are blocked from the scope. Radar beacons have been used for many years in aviation. In the past, airfields had beacons visible on radar much like a non-directional beacon, NDB, but most are now decommissioned. Radar beacons consist of interrogator and responder units operating from different locations. The interrogator transmits a pulse that causes the responder to transmit a corresponding pulse. The interrogator receives the coded return and uses time-lapse and azimuth, or sweep relationships, to display the returns on the display. The time needed for generation of the return pulse causes a range error amounting to 1/2 mile, generally. Beacons are sometimes coded with a mixture of aircraft identification and flight parameters for Air Route Traffic Control Centers, ARC. Aircraft equipped with beacons, like the APN-69, can interrogate and respond to like-equipped aircraft. Beacons, like the APN-69, use a pulse code of up to 6 pulses. The pulse codes are set by the responder aircraft and appear on the interrogator's display. The first pulse is in the relative position of the responder with successive pulses trailing. The range between aircraft is equal to the range of the first pulse, minus 1/2 nm, and the azimuth is measured through the middle of the pulse length. 2 blocking circuits are included in the units to prevent interference from radar on other frequencies or a return of the interrogating pulse. This sometimes prevents a ring around where false azimuth inputs are presented on the display. In such cases, excessive gain causes returns to be picked up by side lobes of the antenna. Figure 7.13 is an example of a beacon return on the scope. Sensitivity time constant, STC, most radar sets produce a hot spot in the center of the radarscope, because the high gain setting required to amplify the weak echoes of distant targets overamplifies the strong echoes of nearby targets. If the receiver gain setting is reduced sufficiently to eliminate the hot spot, distant returns are weakened or eliminated entirely. The difficulty is most pronounced when radar is used during low-level navigation. To make best use of the radar, the navigator is forced to adjust the receiver gain setting constantly. Sensitivity time constant, STC, solves the problem by increasing the gain as the electron beam is deflected from the center to the edge of the radarscope, automatically providing an optimum gain setting for each range displayed. In this manner, the hot spot is removed while distant targets are amplified sufficiently. STC controls vary from one model radar set to another. Refer to the appropriate technical order for operating instructions. Plan display. The plan display is a sector scan presentation that indicates the range and direction of obstructions projecting above a selected clearance plane. The clearance plane can be manually set at any level from 3,000 feet below the aircraft up to the level of the aircraft. Only those peaks projecting above the clearance plane are displayed, all other returns are inconsequential and are eliminated. The sector scan presentation limits the returns to those ahead of the aircraft. The vertical line represents the ground track of the aircraft, and ranges are determined by range marks. Profile display. The profile display, normally received only by the pilot, provides an outline of the terrain 1,500 feet above and below the clearance plane. Elevations of returns are represented vertically, azimuth is represented horizontally. This display gives the operator a look up the valley. The returns seen represent the highest terrain within the selected range. The position of the aircraft is represented by an aircraft symbol on the indicator overlay. Techniques on radar usage. Radars currently in use offer variations of special equipment and capabilities. The following are techniques to use with radar in common situations and with special equipment designed to enhance radar usage. These are basic suggestions that can and should be adapted to specific aircraft. Radar fixing techniques in radar fixing change from operator to operator and most provide accurate results. The following are reminders that affect the fix accuracy if not considered. Radar is an aid to doctor before any radar return can be accurately identified. The operator should be familiar with a chart of the target area. This chart study relies on knowing the approximate location of the aircraft and, therefore, it is essential to radar fixing that the best possible doctor position is ascertained. In examining the area surrounding the doctor on the chart, attention should be given to details like roadways and waterways, as well as the more prominent urban returns. Cultural returns build up along such byways, therefore, discrepancies between the chart, which could be years old, and the display can be more successfully analyzed. Prior to fixing, take care to adjust gain, antenna tilt, and heading marker. If you use a mechanical cursor, ensure its center is aligned with the sweep origin, or risk parallax error. Do not accept a return on the scope as the chosen target unless you have verified it using surrounding returns. Work from chart to scope. If your desired target does not show, but you see a return you think you recognize, go back to the chart and verify it before fixing from it. When obtaining fix readings, remember to compensate for inherent scope errors. If the fix is a multi-range or multi-bearing type, choose the targets to provide the optimum cut. When using multiple targets, read the returns that are changing their values the fastest closest to fix time. With multi-range, a target off the nose changes range faster than the one off the wing. Slant range. Once you identify a return, use it to fix the position of the aircraft by measuring its bearing and distance from a known geographical point. Of particular significance in any discussion of radar ranging is the subject of slant range versus ground range. Figure 7L4, slant range is the straight line distance between the aircraft and the target, while ground range is the range between the point directly below the aircraft and the target. To fix the position of the aircraft, the navigator is interested in the ground range from the fixing point, yet the fixed range markers give slant range. The trick is to determine the critical range below which the navigator must convert slant range to ground range to keep fixes accurate. This range may be determined by a simple formula: critical slant range equals absolute altitude. In K-5 slant range can be converted to ground range, using the latitude and longitude lines of a chart if the slant range table is not available. Set dividers at the slant range distance to the target. Place one point of the dividers at the equivalent, in nm, of the aircraft's altitude on the longitude line. Set the other point where it meets a nearby latitude line. Without moving point, reset the first point along the latitude line at the intersection of the latitude and longitude lines. The distance is the ground range in nm. Figure 7.15, slant range correction charts are provided in figures 7 to 16. Side lobe interference. Side lobes are small extra fields of energy separate from the main beam and are an inherent flaw in any radar. These side lobes are rarely strong enough to generate a return. However, when a large or very reflective target comes into this field, or when the transmitter power increases the size of the lobes, multiple shadow returns may appear on the display. Curved strobes originating at the center of the radarscope are also caused by the side lobes of the radar receiving energy from your radar or others in the same frequency range. Solutions to this problem include reducing the gain or changing transmitter frequencies. Target timing wind. This is a technique for obtaining a wind by using radar targets to provide track and ground speed, Gs, of an aircraft. Figure 7.17, the MB4 computer solution for wind requires true heading, TH, true airspeed, TAS, drift angle, DA, and Gs. The first two can be derived from basic aircraft instruments, indicated airspeed, IAS, and compass. The other two require a target that can be tracked for about 4 minutes and which is preferably within 20 degrees of the radar heading marker. The identity of the target is irrelevant, but it should not be too big to make range and bearing determination vague, or so small that it disappears. Choose a target that has just appeared on the scope and read its range and bearing. Also, start a stopwatch or note the minute and seconds on a clock so elapsed time can be measured. At least 2 ranges and bearings should be taken over a distance of 20 to 25 nautical miles. One technique is to fix at the 40, 30, and 20 nautical miles range marks to space the fixes evenly. At the last observation, stop the watch and determine the elapsed time. On the wind face grid of the MB4, place the grommet over the center mark of the top reference line. Turn the compass rose to the azimuth of the first fix. Using your own values for each of the horizontal grid lines, plot a point representing the range of the first fix, going down. Then, turn the compass rose to the azimuth of the second fix and plot a point, measuring from the top line again, representing the range of the second fix. Repeat for the successive fixes. Figure 7.18, to solve for the wind, Rotate the compass rose so that the three plotted lines are parallel to the vertical grid lines and read the track under the true index of the compass rose. Then, determine the G's by measuring the distance between the first and last plotted points using the grid lines. Using track and TH, find the dA and use the standard MB4 wind solution. Weather avoidance: severe turbulence, hail, and icing associated with thunderstorms constitute severe hazards to flight. You must avoid these thunderstorms whenever possible. Airborne weather radar, if operated and interpreted properly, can be an invaluable aid in avoiding thunderstorm areas. You must be aware of factors and limitations affecting thunderstorm radar returns to get the most out of the radar. Some of these factors are not meteorological and depend on the characteristics of the radar and the way it is used. The same weather target can vary considerably in its appearance from ground mapping mode to weather mode. Navigators must ensure they use the radar as intended for weather avoidance. Primary meteorological factors that affect radar returns are the amount of moisture in the weather target and atmospheric absorption characteristics between the radar antenna and the target. The predominant weather-induced returns on most radarscopes are caused by precipitation-size water droplets, not by clouds. Intense returns indicate the presence of very large droplets. These large droplets are generally associated with the most hazardous phenomena, those with strong vertical currents that are necessary to maintain these droplets in the cloud. It is possible, however, to encounter such strong turbulence in an echo-free area or even in an adjacent cloud-free area, so avoiding areas giving intense returns does not necessarily guarantee safe flight in the vicinity of thunderstorms. Make careful note of all areas forecast to have the potential for hazardous weather. Generally, the map mode of the radar with a moderate amount of gain applied is adequate for obtaining a return from hazardous cells. Sometimes, ground returns hamper detection in the area by hiding the storm. This can occur in mountainous areas where ground returns are similar and air mass lifting action breeds the cells. For these reasons, raising the radar tilt or switching to pencil beam, or both, are techniques that aid weather detection. There are two types of weather avoidance with radar: avoidance of isolated thunderstorms and penetration of a line of thunderstorms. Avoid an isolated return by first identifying it and then circumnavigating it at a safe distance. After detecting a weather system, determine its extent. Analyze the weather's layout relative to planned track and decide either to deviate around it or penetrate the line. If the system is complex, remember your deviation could worsen the situation by flying into a sucker hole, where a solid system could surround the aircraft. Sometimes, what seems to be a good heading at short range seems foolish when viewed at long range. Remember that turning around is always an option, and art can sometimes assist in weather analysis. A simple technique for flying around weather at a preferred distance, say 20 nautical miles, is the flying disc technique. Imagine the aircraft as a disc defined by the 20 nautical miles range mark on the display. The heading marker is the nose of the disc. Draw an imaginary tangent from the disc to the edge of the weather, or use a pencil or plotter. Turn the aircraft the same number of degrees that it would take to get the heading marker to fire parallel to the tangent. After the turn, recheck the heading in the same manner. This technique works best with a scan of more than 180 degrees. Figure 7.19, penetration of a line of thunderstorms is a last resort and presents a different problem. Since the line may extend for hundreds of miles, circumnavigation is not practical or even possible. If no other course of action exists, the main objective is to avoid the more dangerous areas in the line. Figure 7.20 shows an example of frontal penetration using radar. An ISO-echo-equipped radar can discriminate between the safe and violent areas. Without it, decreasing the gain works to highlight the worst areas by leaving the densest water cells as the last returns on the display. Upon approaching the line, the navigator determines an area that has weak or no returns and that is large enough to allow avoidance of all intense returns by the recommended distances throughout penetration. The navigator directs the aircraft to that point, making the penetration at right angles to the line so as to remain in the bad weather areas for the shortest possible time. Avoid the dangerous echoes by a safe distance. Penetration of a line of severe thunderstorms is always a potentially dangerous procedure. Attempt it only when you must continue the flight and cannot circumnavigate the line. Always advise ARC of your intentions when deviating from your flight plan route. Heading marker correction for optimum accuracy. It may sometimes become necessary to correct the bearings taken on the various targets. This necessity arises when the heading marker reading does not agree with the TH of the aircraft when azimuth stabilization is used, or the heading marker reading does not agree with 360 degrees when azimuth stabilization is not used. For example, if the TH is 125 degrees and the heading marker reads 120 degrees, all of the returns on the scope indicate a bearing that is 5 degrees less than it should be. Therefore, if a target indicates a bearing of 50 degrees, add 5 degrees to the bearing before plotting it. Conversely, if the heading marker reads 45 degrees when the TH is 040 degrees, all of the scope returns indicate a bearing that is 5 degrees more than it should be. Therefore, if a target indicates a bearing of 275 degrees, subtract 5 degrees from the bearing before plotting it. The greater the distance to the target from the aircraft, the more important this heading marker correction becomes. Chapter summary. This chapter discussed the history of radar navigation and how radar technology has improved throughout the years. Basic radar principles are explained, including the different types and how the components work. Scope interpretation is introduced in this chapter along with radar reflection. The many variables affecting radar return are discussed, such as varying terrain and weather. Inherent scope errors are explained along with the different radar enhancements that help the navigator. The many different uses for the radar are discussed and how each can help the navigator navigate through different terrain, weather, and altitude changes.